Transformers are capable of receiving AC power at one voltage and delivering it at another voltage. In this way, they help achieve better transmission efficiency while transferring the power over longer distances. In this video, we will go through the working and construction of a three-phase transformer by starting from its simplest form. The basic working principle of a transformer is simple: electromagnetic induction. According to this principle, a varying magnetic flux associated with a loop will induce an electromotive force across it. Such a fluctuating magnetic field can easily be produced by a coil and an alternating EMF system. A current-carrying conductor produces a magnetic field around it. The magnetic field produced by a coil will be as shown in the figure. With the fluctuating nature of the alternating current, the magnetic field associated with the coil will also fluctuate. This magnetic flux can be effectively linked to a secondary winding with the help of a core made up of ferromagnetic material. This fluctuating magnetic field will induce an EMF in the secondary coils due to electromagnetic induction. Since the turns are arranged in a series, the net EMF induced across the winding will be the sum of the individual EMFs induced in each turn. Since the same magnetic flux is passing through the primary and secondary coils, the EMF per turn for both the primary and secondary coils will be the same. The EMF per turn for the primary coil is related to the applied input voltage as shown. As a result, the induced EMF at the secondary coil is expressed as follows. This simply means that with fewer turns in the secondary than in primary, one can lower the voltage. For the reverse case, one can increase the voltage. But since energy is conserved, the primary and secondary currents have to obey the following relationship. Three-phase transformers use three such single-phase transformers, but with a slightly different coil configuration. Here, the primary and secondary coils sit concentrically. Two more such windings are employed in a three-phase transformer. Transformers with high power ratings generally employ a special kind of winding, known as a disc-type winding, where separate disc windings are connected in series through outer and inner crossovers. The low-voltage windings are connected in a delta configuration, and the high-voltage windings are connected in a star configuration. Thus, the line voltage further rises to root 3 times at high voltage side. This also means that, from a three-phase step-up transformer, we can draw 4 output wires, 3 phase power wires, and 1 neutral. High-voltage insulated bushings are required to bring out the electrical energy. The core of the transformer is made of thin insulated steel laminations. Such steel laminations are stacked together, as shown, to form three-phase limbs. The purpose of thin laminations is to reduce energy loss due to eddy current formation. The low-voltage windings usually sit near the core. Various kinds of energy loss happens while transferring power from the primary to secondary coil. All these energy losses are dissipated as heat. So usually the transformer is immersed in a cooling oil to dissipate the heat. The oil dissipates the heat via natural convection. Oil in the tank will expand as it absorbs the heat. A conservator tank helps to accommodate for this volume change.